Physics video lecture, Physics 203 video lecture 9. And we've been working on theory of small oscillations. I have one more interesting example to wrap things up. And then we'll move on to other things. So we'll start the central force problem. So many things to do this semester. But one more problem in small oscillations. And this is going to be the linear chain. Linear chain. So here's the idea. We have just a whole bunch of masses and springs. Ideal springs, point masses, right? So on and on. And we're going to have a total of n of these, and n's a pretty large number. But we can imagine a one-dimensional motion, and here's an x of 1, and then we move on a ways. In particular, we have x of j plus 1, x of j minus 1. J minus 1, like that, okay? And they all have the same mass. And we all have the same spring constant, okay, and so forth. Okay, same mass, same spring constant everywhere. So what we want to do is get the Lagrangian, get the equations of motion, and look at them, see what we can do. So it'll be the same construction we had with the 2 masses, or we could have had with 3 or 4 masses. The kinetic energy is no problem. We have 1/2 sum mx of I dot squared. I equals 1 to n. For the potential energy, with the exception of the masses on the end here, we have k x of I plus 1 minus x of I squared, right? There's always the difference, and they were storing energy in the springs. So here we would take I equals 1 to n minus 1, and then we'd have the springs on the end. So on the left end we'd have a 1/2 k x1 squared, and on the right end we'd have a 1/2 k xn squared. So we actually have all of the kinetic energy and the potential energy. And if this thing is long enough, we're not going to worry about the endpoints. Okay? So we're going to do our Euler-Lagrange equation for this jth particle. Okay? So we have Lagrangian is just t minus u, and we're looking at d dt partial L with respect to, I think I'll use the subscript nu, dx of nu dot minus dl dx of nu equals 0. Okay, this is the case where you want to have everything in front of you there. So we're doing the derivative with this arbitrarily chosen point somewhere in the center of the chain. And the derivatives with respect to x dot, of course, only differentiate kinetic, and the derivatives with respect to the coordinates just differentiate the potential energy. So we could also say d dt dl, or d capital T dx nu dot is equal to, we always got those 2 minus signs, so e minus u minus du dx of nu. And of course, when you put it that way, you see, this is Newton's law, right? So let's go ahead and write this out. We have mx of nu second derivative. Now, for the potential energy, we have to be a little more careful, right? This one here was trivial. We picked the newth, and then 2's canceled, gave it one more time derivative, 2 dots. For the potential energy, you got to be a little more careful. And looking at this thing here, we see we're going to have du dx of nu. We have x of nu plus 1 minus x of nu. So we're going to pull out as a, okay, we're going to pull out a k x nu plus 1 minus x of nu. But we're differentiating with respect to x of nu, so it's got a minus sign there, and the inner derivative gives us another minus sign. Okay. Now the thing is this: we also have here. Let me go ahead and write that down. We have in particular 1/2 k x nu plus 1 minus x nu plus 1/2 k x nu minus x nu minus 1. So this x of nu shows up twice up here. And I just picked off one of them, and now I'll deal with that one. These were squared. So I picked off this one. Now here it is going to give me again plus k x nu minus x of nu minus 1. So that's what we're actually looking at. And our differential equation written out, coupled differential equation, we'll get rid of the minus sign here. We will have minus times this, so we'll have k times x nu plus 1, and then we'll have x nu, so minus minus, we'll have minus 2 of these x of nu's. We have one here as well. And then we have plus x of nu minus 1. So there's our differential equation. The motion of one of them depends on the motion or the position of 3 masses. Position of itself plus its nearest neighbor. So that makes complete sense. We'll put a box around here. Can't declare victory yet, though. So what we're going to do next is consider the continuum limit. So next, we want to investigate the continuum limit and that would be where these masses are distributed, you know, in ever smaller amounts, ever closer together. So eventually this mass, you know, we take half the mass and place it in 2 places closer together, and then we take half of that, place it closer together, and eventually it would be smeared out as a continuum along the x-axis. So to get started on that project, first, we're going to define, we're going to let u of x of nu and t be the displacement be equal to, I'm just going to write x of nu of t. Well, that doesn't seem to be, you know, it's appearing in here. What we're thinking of this as is the displacement at position x of nu. In other words, we now think of this as an x-axis, And this position is actually the position along that number line, so to speak. And the displacement, which we were also calling x sub nu because it was the displacement of that particle around its equilibrium position, we're now thinking of the displacement of that particle with respect to its original location. So I should put a couple of words there. I'll put this parenthetically, be the displacement of the newest mass, which is what those point masses are, right? And then we'll turn this, so this x of nu is actually just part of the continuous x-axis. From its position. So now we're on this continuum, and immediately, okay, right here. Now we can interpret m x nu second derivative as m d squared with respect to time partial of u of x and t, okay? Because you're at a position x, and I'll leave the subscript in here for now, we'll get rid of it later, it's common. You're at a position x and you're saying, what is the mass from that position doing, right? It's moving, so that's its displacement. So that takes care of the left side of this equation. We have to deal with the right side now. That's interesting as well. So yeah, we'll hold on to that. Yeah, so the right side of our differential equation turns into a very interesting difference quotient. So let's see how this construction goes. Yeah. So for x nu plus 1 minus 2, x nu plus x nu minus 1, consider, I'm just going to draw this out very carefully. So this is x sub nu, minus 1, x sub nu plus 1. Those are those positions along the number line. And this is the object that we're analyzing. So this needs a separation distance L. So we now have separation distance L between each of these, and we can interpret this as a difference quotient in the following way. So first of all, I'll go right underneath here. We have u of x of nu plus L minus u of x of nu. Okay, put brackets around here. That's one of these minus u of x of nu minus u of x of nu minus L. Okay. So since we're in the middle here, x nu sub 1 is the displacement of the function at x of nu plus L, right? X of nu plus L. Minus one of these is u of x of nu. And the other one minus the other one here, that's the second one, and then minus the negatives is plus this right here. Okay. So this construction, okay, going to continue by taking L and writing this here again, U x nu plus L minus U of x nu minus x nu minus L. So I haven't changed anything, but I'm dividing this, multiplying and dividing by L. So now what I have, now I seem to have a difference quotient, and let's go ahead and use red here. X nu plus L, that's not L, that's supposed to be L over 2, yeah. Otherwise I'd have too much minus L over 2. Not so fast, L, that's true, okay. Next step. So here's a difference quotient, and this one here, take it out to the right here. This one here, we have L and U of x nu plus L minus U of x nu divided by L. That is a difference quotient for a first partial derivative. Okay, so we're ending up with L d u dx x nu plus L over 2 and minus du dx x nu minus L over 2. Okay, we're always taking the middle of these intervals. That gives us a high accuracy. So if I do this now, squared and divide by L again, what do I have? This is a great construction. So first of all, I multiplied by L over L, that's 1. Now I incorporated that L into my partials, therefore I multiplied by L over L again, and what you see is I have L squared, I'm going to write approximately because these are approximations, L squared d squared u dx at x sub nu. Because now this is a difference quotient centered on the middle there. So I have L squared times a second partial derivative, and that's what this difference object means. In fact, if you do if you do numerical differential equations, you'll actually implement exactly these kind of strategies here. So if you want a second derivative, you'll actually work back and implement this formalism. So yeah, that's an interesting construction. So take a good look at this. I think you'll enjoy seeing these derivatives come right out. See, for the first one, if you're looking at this here, you're evaluating here, and dividing by L, multiplying by L, means that the difference quotient for the function in the middle. Okay, so that's how you got your first derivative, and there, and then this step down here, which I'm going to put as our final result, was the difference quotient for these 2 points, and therefore that's the good approximation to the derivative right there in the middle. So yeah, we fair and square get an approximation for second derivative in x, and we already had second partial derivative in time. So let's see what we want to erase and what we want to leave up. what I have to do is draw my linear chain again anyway. So let's go ahead and erase all this. Yeah, leave enough space and you can figure out exactly what I did with the progression from the difference expression to these difference quotients and then their interpretation as the second derivative there. So what we now have, we have for that linear chain, d squared m d squared u dt squared. I'm just going to put an approximate sign, k l squared d squared u dx squared. Okay. So we haven't yet taken the limit. Before taking the limit, right? These are all difference quotients. In the limit, you know, what limit are we talking about? L goes to 0. L goes to 0 is what turns these things into derivatives. And like I said before, they're excellent approximations because they're centered right there. In both cases, they're centered. So, taking the limit L goes to 0. But it doesn't look like we can take the limit L goes to 0 because that looks like it's just going to kill this here. Okay. However, we can, so what we do next is we're going to write d squared u dt squared equal, not equals, approximately k l squared over m d squared u dx squared. And what we want to do is take that limit. L goes to 0. This is an interesting trick. We just have to interpret what we're doing. So let's look at our chain again. We've got k m. In fact, I'm going to draw this larger so that we can see it. Okay, we've got m. Okay, so we've got these point masses m, m. We've got the spring constants here, and the separation of each of them is this little L. Now what happens is this. We imagine distributing this mass, cutting it in half, so distribute masses, mass m into m over 2 plus m over 2, and they're now separated by L over 2, with L over 2 separation. Okay. And something interesting happens. This KL squared over m goes to 2k L over 2 squared divided by m over 2, sorry, divided by m over 2. And the reason is this: if you take an ideal spring and nail it down and just use half of the spring, you get twice the spring constant. You can prove this with really elementary Newtonian mechanics, or you can say we demonstrated that with our 2 masses, 3 springs, the 2k prime phenomenon. It just came out of that calculation. It's definitely the case. Half of an ideal spring has twice the spring constant, and we've taken the original mass and divided it in 2 and placed it at the midpoint there. So our next thing was that we had m over 2 everywhere, m over 2 m over 2 everywhere, and the separation distance was L over 2. And look what we get. We get K L squared, get the 4, 2, 2, okay, 4, 4. Fantastic. K L squared over M. So if you do it again, and again, you're always retaining this value of that constant, which is kind of amazing. So KL squared over M is just constant in the continuum limit. As we do the continuum limit, okay. So we can get rid of the approximate sign here, and we can write d squared u dt squared partial equals v squared d squared u dx squared. And a little dimensional analysis shows that this actually is a speed squared. Okay. And what we have there is the wave equation. So what we get in our chain here is pulses passing through the chain, and in the continuum limit, we get continuum pulses passing through the chain, behaving a wave equation. So that's pretty good. We're going to encounter the wave equation later in the semester in 3 dimensions, but right now we have it in 1 dimension. So it's a 1-dimensional wave equation. I'll just say a couple words about its solution. You've studied wave equations before, and we're going to study them again later in the semester. So yes, we've obtained a wave equation. So the linear chain obeys a 1-dimensional wave equation in the continuum limit. So we have d squared u dt squared partial equals v squared u dx squared. And solution let u of x and t be equal to, I'll use a function, I'll use the same name of the function, u of x plus or minus vt. So u is just a simple scalar function, and we can imagine we've got a pulse, and at t equals 0, this is just u of x, and this is the x-axis. But for t not equal to 0, you can see that x minus vt corresponds to this pulse moving to the right, and x plus vt corresponds to the pulse moving to the left. And so we go ahead and let that there be the case, and then d squared u dt squared. Now we're just going to have u double prime of x plus or minus vt times plus or minus v squared, the inner derivative, and that equals u double prime, that equals plus or minus v squared. And my second partial with respect to x, of course, is just going to be u double prime as well. So second partial with respect to x. Okay. So yeah, that is a traveling wave solution in 1 dimension. Now it's a pulse of the displacement u, which is along the line. By the way, a very similar derivation, starting with the same differential equations, can actually be done for pulses that are transverse. So our example is a longitudinal wave. I'll just write here, same derivation, beginning with the Euler-Lagrange equations, can be used for both. You just relabel things a little bit different for both longitudinal and transverse waves. Good. So that wraps up our small oscillations, and you see it led us into a wave equation, and we're going to pick up the study of wave equations much later in the semester when we get to fluid mechanics. Although, you know, the semester is moving right along, so we have to move along too. Let's see. Good. So that ends this chapter, small oscillations. And the next thing we're going to talk about is the central force problem, which is a great one that we all need to review, always. Okay, so yeah, we will return to the wave equation in 3 dimensions when we get there, and then we'll study more than just, you know, than just this really basic solution. And we'll go a little deeper into the wave equation. I'll put a note here. This is what you all should do. Check that the units of KL squared over M really are equal to meters per second squared. So here the M stands for meters seconds. Here the M stands for kilograms, right? One of those things. That's kilograms right there. So check the units. Just leave a little room in your notes, check the units, make sure you agree that we actually have a speed squared, as has to be the case. Yeah, okay. Yeah, so we've done variational calculus, Lagrangian mechanics, general thing, then this small oscillations as a very important application of Lagrangian mechanics, and we took it to the derivation of the wave equation in 1 dimension. Okay, so our next topic leaves that. It is central force, and central force we want to take through to the Kepler problem. Remind ourselves of that. After that, we'll come back to Hamiltonian mechanics, right? We've just done Lagrangian mechanics. We'll come back to Hamiltonian mechanics and pursue the formalism quite a bit further. In fact, let me just put that up on the board and it is a list where we're headed. So next, central force problem. Central force, all the way through the Kepler problem, a couple of interesting applications. Then, Hamiltonian mechanics, and other formalism, canonical transformations and stuff, till we can get to Hamilton-Jacobi theory. I'm going to have to start counting our lectures down so we have time for everything, because we actually want to then do some fluid mechanics, continuum mechanics, because the fluid mechanics is going to run us up, you know, we're going to end up with waves And we're going to find a wave formalism that looks just like this. Okay, so we've got a whole program to unfold, but the central force problem is just such an important problem for just doing it to make sure we remember all about it. Okay. The real formalism of the course, Hamiltonian, Hamilton-Jacobi, and other interesting stuff as well. Good, so central force. So we'll begin with two bodies. We know that the Euler-Lagrange equations are Newton's equations for point masses in 3 space. So we're going to begin with two bodies in space, and we will label their masses m1 and m2, and we'll label their positions r1 and r2. Okay, as two vectors. Yeah, let's see. We're going to do the whole thing? Yeah, I think we will. So I'm also going to define this vector here, r is equal to r1 minus r2. And I'm even going to put a little star here indicating the center of mass. Okay. So what we're going to do is the two-body problem in center of mass coordinates. Center of mass coordinates. We want to find center of mass coordinates, and then we can express both of them in terms of this vector r here. So what is the center of mass? R sub center of mass is m1 r1 plus m2 r2 divided by m1 plus m2. That's the center of mass. If we want to have center of mass coordinates, we can let that be the origin. And r center of mass, origin, so that is equal to 0. So we have m1 r1 plus m2 r2 is equal to 0. It's the numerator up there, and r is equal to r1 minus r2. So we have two equations, and we can figure this out now. So m1 and r1 will be r minus r2, no, r plus r2. So m1 r plus r2 plus m2 r2 is equal to 0. Therefore, we have m1 r plus m1 plus m2. R2 equals 0, and we have r sub 2 is equal to minus m1 r divided by m1 plus m2. And it's got a minus sign in front of it, m1 plus m2. So you can see r sub 2 is pointing opposite r, which is pointing to the left, so pointing to the right as it should. And we can then immediately construct r sub 1 is just going to be m2 over m1 plus m2 times r. Because we can just substitute 1s and 2s, and Notice that this one has the opposite sign of the other. So those are our results. So if we know R, then we know R1 and R2. Okay, so good. We have the coordinate transformation. The next thing, we have this central force, so we're looking at M1 R1 second derivative equals a force, and M2 R2 second derivative equals minus that self-same central force. Okay. Okay, what we're going to do next is turn this into we're going to turn this into a one-body problem. So we're going to have M1, and then R1 second derivative is M2 over M1 plus M2 R second derivative. And the second one here is going to, so this is going to be F. Second one is going to be M2, and R2 second derivative is minus M1 plus M2 R second derivative is equal to minus F. So now let us subtract one from the other. Subtract one from the other, these add, okay? Because this one has a minus sign. So we have M1, M2 over M1 plus M2 times 2R second derivative is equal to F minus negative F. 2 times F. This F here is our central force. We'll talk about it in a moment. But we've arrived, 2's cancel, at an important equation. So what we have is the reduction of the two-body problem to an equivalent or to an effective one-body problem. So now M R second derivative is equal to F, where M is the product of the two masses divided by the sum. That's called the reduced mass. Reduced mass. R is this difference vector. And of course, this difference vector is along these two particles. And F, we're going to let be a central force. So it's going to be proportional. It's going to have its direction R over R. But let's put it this way. The force of R1 and R2, but it has the form. It has the form that it's going to be proportional to R1 minus R2 divided by the magnitude. So that's just a unit directional vector, which is R over R. So that's your R over magnitude R for the moment. So that's your central force type of problem. It has just simple Newton's law here. Okay, now we already have the conservation laws for this system, but I'm just going to show you how they come into play explicitly here directly. Okay, so I can erase this. So we have central force F equals minus the gradient of U, and we already know it's expressed in terms of just the difference, okay? Function of the difference. So we have m r second derivative equals minus gradient u of r. Now you'll notice I took away the vector there. The potential is now a function of the magnitude for a central force, where gradient u of r is equal to u prime of r times the unit vector r over r. This is just a fact of calculus. Okay. So because we have a central force problem, this is the form of our problem right here. R second derivative, gradient u of r. This is because we have conservation of energy, which a central force equation has. And I was wondering if we practiced this stuff earlier on. R is equal to the root x1 squared plus x2 squared plus x3 squared. X, y, and z, right? We're in free space. D u dx sub k, okay, just one of those components, is going to be u prime of r times dr dx sub k, because that's just the chain rule. Is going to be u prime of r, and then dr dx sub k is going to be 1/2 root x1 squared x2 squared. And then the inner derivative here is going to be 2x sub k. 2's canceled. Set this down. Continuing, so we'll have the u prime of r, and then this thing here is x sub k over r. And so since we have this, for all three components of it, it'll be vector r divided by magnitude r. Okay. Good. Put a minus sign in front of it and you have the force. Okay, so we have that reduction to a one body problem. Remember, this is the reduced mass for a two body problem. It could be just the mass for a central force problem in general, but for a two body problem, it's that reduced mass right there. Product divided by sum. Good. Yeah, let's see how far we want to take this. Good, we'll take a few more minutes to wrap this up. So once again, I'll show you where we are now. We started with two bodies, and I'll draw their positions again, M1, M2, R1, R2. Let's imagine that the center of mass is really close to M sub 2. Right, I'll draw this vector in red. This is our difference vector, R1 minus R2. So imagine the center of mass is really close to M2. So M2 is much larger than M1. So consider reduced mass when M2 is much greater than M1. Okay. So now we're just writing down M equals M1, M2 over M1 plus M2. So M2 is much greater, so the M1 in the denominator is negligible. So it's really approximately to M1, M2 over M2. They cancel. So what we have is the reduced mass is just approximately equal to M1. So this could be our Earth orbiting the sun, okay? And the center of mass would be very close to the sun, or perhaps inside the sun even. Okay. And our equation up here would be the mass, almost the mass of the Earth, M1, times that position derivative, second derivative, would be equal to the force, Newton's law of gravity force. Okay. So this formalism is really nice because any combination of masses now works. You could have a system of equal masses. Say you had a double star system, in the center of mass, they're about the same mass, center of mass is right in the middle of them, and still the same formalism holds, okay, with just different values. If the masses are the same, then you can see the reduced mass is half. And that's why it's called reduced, it's always less. So this example here is important for understanding the reduced mass. And then in the limit of M2 being much, much larger than M1, then it's, as you know, then this center of mass goes into M2 and it's as though M2 were fixed and M1 is simply moving. But in the case where you have this situation here, I'll just put a note on the orbits, then remember R2 and R1 are expressed in terms of R, and so you would have, I'll put the center of mass there, there's the big mass, there's the little mass, and they would both be orbiting, say in the Kepler's case, or a circular orbit, they would both be orbiting their common center of mass. Okay. So your R sub 2 would be much smaller, your R sub 1 would be much larger. Okay. But the solution to that problem, two-body problem, is an effectively a one-body problem. So let's see, that clarifies those issues. I think I'll do one more point and then we'll have a good place to stop. We had conservation laws. Energy we've already used. We'll use it again actually. We've used it in the sense that we wrote down a potential energy. Energy, linear momentum, angular momentum. Let's look at the angular momentum. We know it's conserved Let's see the conservation explicitly in terms of a central force problem. So we would have, we'll call it L is equal to R cross MR dot. R cross P, right? R cross MR dot. dl dt is R dot cross MR dot. Just doing a product rule now, plus R cross, parentheses here, MR second derivative. Here we have two parallel vectors, cross product, that vanishes. Here we have something interesting. We have R cross MR second derivative, but we had a central force. So F of R, R over R, right? That's the form for a central force, just like our U prime of R, R over R. In fact, I could write, just to be keeping in with that, minus U prime of R, R divided by R. But this expression also has parallel vectors, so it also vanishes. So we get a 0, and that means L is constant. That means L is constant. That means the magnitude and the direction of the angular momentum are conserved. Angular momentum is conserved, therefore magnitude and direction. And my last thing then, if the magnitude and direction of the angular momentum are conserved, the motion is restricted to a plane. So the central force problem motion, because of the angular momentum conservation, because L equals constant, the motion is restricted to a plane. Restricted to a plane. And what we'll start off with next time is plane polar coordinates. So that's going to justify the use of plane polar coordinates. Good, that's what we'll start with next time. We'll have our central force problem set up. We'll set it up in plane polar coordinates. We've got conservation of angular momentum. And so then we'll be moving right along. Okay, see you all next time.